In this video, we're going to relate linear transformations to invertible matrices. So remember, whenever you have a matrix, you can build a linear transformation out of it and vice versa. So now the question is, if we have an invertible matrix, what does that say about the transformation? So before we actually relate it to matrices, let me define what an invertible transformation is. That's where we start here. So if we have a linear transformation from Rn to Rn, we say that it's invertible if we can find another linear transformation from Rn to Rn such that these conditions hold. If I take a vector and I plug it into T, and then I take the resulting vector and plug it into S, I get the original one back. And similarly, if I take a vector and plug it into S first, and then plug the result into T, I get the original vector back. And this is for every single vector in Rn. So if these conditions hold, then I say that S is an inverse of T, and we say that T is invertible. Now there's a nice relationship between invertible matrices and invertible linear transformations. So let's say T is a linear transformation and it has standard matrix A. And remember what that means. Having a standard matrix A, that just means T of X is defined to be A times X. And so in this case, let's also assume that A is invertible. So the goal is to show that T is also invertible, and I want to see exactly what the inverse of T is. So if A is invertible, I want to define S to be the linear transformation with standard matrix A inverse, which I know is possible because A is invertible. And so now let's see what happens. Let's show that S is actually the inverse of T. So if I do S composed with T, and I plug in a vector, well, T of X, again, is defined as A times X. So now I have this vector AX, and I'm plugging it into S. But S is defined by this relationship, this equation. So I have to multiply whatever I plug into S by A inverse. So I have A inverse times A times X. And of course, A inverse and A are inverses, so I just get X. And similarly, if I do T of S of X, similar thing happens. I'm going to have T of A inverse times X, which gives me A times A inverse times X. A times A inverse is the identity. Identity times X is just X. So this tells me that S is the inverse of T. So if T is a linear transformation and the standard matrix is invertible, then T is invertible. And it turns out that the opposite's true too. If T is invertible, then the standard matrix has to be invertible. And you could show that by going through a similar process here. So here's a summarization here in this theorem. If we have a linear transformation with standard matrix A, then T is invertible if and only if A is invertible. And moreover, in the case when T is invertible, the standard matrix of its inverse is A inverse. That's what we just discussed in the previous slide. We can also relate this notion of invertibility with one-to-one and onto. Now you might have to think back to what one-to-one and onto transformations are, the basic definitions. And if you don't really remember them, I encourage you to look back to the relevant video. I think it appeared maybe in section 1.9. But what we see from this theorem is that T is invertible if and only if A is invertible. Its standard matrix is invertible. That's what the theorem says. And if we think back to a theorem from a previous video, when we talked about invertibility, one of the theorems we saw was that A is invertible if and only if AX equals B has a unique solution for every single B. So any B that you choose here, this has a unique solution, has exactly one solution. Now comes the point where you have to think back about one-to-one and onto, because this having at least one solution is what it meant for t to be onto, and this having at most one solution was what I meant for t to be 1 to 1. So in this case, we have exactly one solution. So that means it's both 1 to 1 and onto. So we have this nice other description of invertibility. A linear transformation is invertible if and only if it is 1 to 1 and onto. Let's see a quick example of this. Let's say I have this linear transformation from R2 to R2, and what this does is it rotates points by an angle of pi over 2 about the origin, and it goes counterclockwise. So we saw in a previous video that the standard matrix for any kind of rotation that looks like this is of this form, where you plug your angle into these sines and cosines, and in this case you get this matrix. This is the matrix that gives this linear transformation. So my first question here is T invertible? Can you invert this linear transformation? And there are different ways to approach it. You could try to think about it geometrically. Is there something you can do to undo this linear transformation? But I want to do it algebraically. I want to use the theorem from before, because this is invertible if and only if this matrix is invertible. So let's use that. Well, let's look at A. So T is invertible if and only if A is invertible. So the question is A invertible? Well, there are different ways to show that. One way is to show that if you row reduce this, to put this in reduced echelon form, you get the identity. Another way is to compute the determinant, show it's non-zero. That's probably the simplest way. If I look at the determinant of A, so the determinant, the way that worked, I multiply these two entries, I multiply these two entries, and I subtract. So I have 0 times 0 minus -1 times 1. So I get 1. This is not 0. A is invertible. So determinant's not 0, A is invertible, that implies T is invertible. So I didn't have to work with this function at all, this transformation at all. I just had to work with this standard matrix. The second question I can ask is, what is the standard matrix for the inverse? We now know T is invertible. Well, what's the standard matrix for it? Think back to the theorem again. Theorem said that the standard matrix of the inverse is nothing but the inverse of A. So that's all we have to do. We just have to compute the inverse of A. It is A inverse. And now we could think back to the formula for the inverse of a 2 by 2 matrix. I do 1 over the determinant, which I know is 1, and I multiply by this matrix obtained by swapping these two positions and negating these two positions. So the inverse is given by this matrix. Here's the final part. Let's describe the inverse of T geometrically. Now I did this in blue because I'm not going to do this in this video, but I urge you to think about it. And you can ask your instructor about it in class if you want to see what happens geometrically. And there are different ways to do it. I mean, one way is we know that T inverse corresponds to this matrix. So maybe you could try to understand what does this matrix do to points in the xy plane. Or you could think about it going back to this definition of what T was. Remember, when you have an inverse function, if you compose your inverse function with the original function, it's supposed to undo what the original function did in some sense. It's supposed to, let me write that down. If you do T composed with T inverse of x, the vector x, you're supposed to get x back. And if I do it the other way as well. So T is a rotation by pi over 2, so geometrically, what would T inverse have to do to get points back to where they started? And then once you describe it geometrically, maybe you could think about what the standard matrix would be and make sure it corresponds to this one. So think about part C. It's a fun one.